Dahmani. He will be giving his third lecture.
So thank you. I resume the last lecture of this mini course, or what this is. And this is about the conjugacy problem in out F3, because in the title that was here before, but it's no longer here, it was mention of automorphisms of three groups of low rank. And for the moment, we didn't really use any consideration of the rank of the free group being low. And so here, it's what I mean by low is less than 3. So this is a joint work with Stefano Francavilla, Armando Martino, and Nicolas Twican. And first, there is even lower than F3, there is F2. Okay, you could say there is even lower, there is F1, which is Z, and we all know the automorphisms of Z, both of them. So, but okay. First consideration, what about actually out F2? And if you remember, oh, that's a question, I suppose. If you remember at the beginning of the first lecture, I told you about the Nielsen automorphisms. And I told you about the Nielsen automorphisms that were a guarantee that the map on GL2Z is surjective. So what is this map? Just a reminder. So look at the abelianization. This characteristic quotient induces some map at the level of automorphism groups. And so it induces, so the map induces another map out F2 on out Z square. It is surjective because we know that here we have the Nielsen automorphisms and they map on elementary matrices that generate out Z2, which is isomorphic to GL2Z. And also, because we are in the very low rank, it is also injective. Why is that? Just very briefly, if I send, if I am in the kernel of this map, it means that I have to deal with an automorphism that sends A to an element that is conjugate to A, B to an element that is conjugate to B. So after a first conjugation, I can assume that it sends A to A, and then it sends B to an element conjugate to B still. And because it has to be an automorphism, those two elements have to generate the free group generated by A and B. And so you can work out that it has to be conjugate to B by an element of the group generated by A. And so by, again, a conjugation, you find that after composing by inner automorphism, it is the identity. So this shows that it is injective. No. GL2Z is a group of automorphism of Z square. So the automorphism sending A to A inverse and B to B is mapped on a matrix that is not in SL2Z. -1, 0, 0, 1. But I mean, SL2Z will come into the picture in a second. So let me move here. So So out F2 is isomorphic to GL2Z. And GL2Z, actually, yeah, it's really coming in a second. So GL2Z possesses a finite index subgroup that is SL2Z. It's of index 2. And SL2Z is a very nice group. It's an amalgamated free product of finite groups. So in particular, it's virtually free. So the group GL2Z is itself virtually free. And so in principle, it's not difficult at all to solve the conjugacy problem in GL2Z because it's a hyperbolic group, it's virtually free. So really, in a concrete point of view, not concrete, I'm losing my word, sorry. In a pictorial point of view, we can draw the tree associated to this amalgamation. And the usual place to draw it, by the way, is to see SL2Z acting on the hyperbolic plane. I can't resist to draw the picture. It's a picture that is very fun to be drawn. So here is a hyperbolic plane, the upper half model. And if you look at the unit circle and the arc between on the unit circle between exponential 2i pi over 3, and it's symmetric. And you look at its orbit for the group acting, for the group SL2Z acting on H2 by Moebius transformation, then it will start to draw a nice tree. So H2 is just the complex number, the model of H2 I use with imaginary part strictly positive, and the action of A, B, C, D on Z is by the Moebius transformation A, Z plus B over CZ plus D. And when I look at the orbit, so here I have to take AD minus CB equal 1 to preserve the upper half plane. And when I look at the orbit, this draws this tree that I can continue drawing. It stretches to infinity, of course, left and right, and it's approaching every point on the real line. So we have a group acting on the tree, and we can understand the conjugacy classes of this group through these actions. Some of them correspond to elliptic elements, fixing a point. Some of them correspond to loxodromic element, preserving a line, and their conjugacy class will be described by this all the invariants that we can find here. Okay, but that's a strange way to present the conjugacy problem in out F2 after all I said to you earlier. It looks like I'm taking advantage, and it's the case, I'm taking advantage of some special geometry on the group out F2, and not at all on the what I talked about yesterday. And remember, what I talked about yesterday was about semi-direct products of F2 by Z, and checking the conjugacy classes of automorphism by comparing those semi-direct products. How about, sorry, I didn't write the conclusion here. So the conjugacy problem in out F2 is solvable by easy geometry on out F2. But why if we don't want easy? What if we don't want easy? What about comparing the semi-direct products so you're given two automorphisms and you have two semi-direct products, F2 semi-direct by phi and F2 semi-direct by psi. That's what I explained here. So here I use GL2Z to solve the conjugacy problem. It's virtually free, it's hyperbolic, life is easy, and we are done. We can have coffee.
The conjugacy problem is not easy in any matrix group?
Easy, well, okay.
Yeah, I thought that would be...
No, the answer is no. It can be solved. I mean, in any matrix group, you have to agree with, in lattices, it can be solved, but it's no way easy. No, it's no way easy. You have to find, so, okay, conjugacy, I should say that. Conjugacy of matrices, yeah, we learned that in undergraduate, right? Yeah. But here is a conjugacy in GL2Z, meaning you want the conjugator to be with integral entries. Still, it's manageable there, but with other GL and Z, it becomes a challenge. And in other group of matrices, like, I don't know, other lattices, somewhere, I don't understand them. Yeah, you want the conjugator to be in the lattice, and that's a challenge. Okay, so now we're convinced that actually everything there was easy and nice. So I proposed something that did not look neither easy nor, well, perhaps it was nice, I don't know. But not easy, comparing the semi-direct products, which are suddenly big groups. And for that, remember, I said that these semi-direct products were relatively hyperbolic, and everything was going to happen in the polynomially growing part of F2 for the automorphism phi and psi. So, first question, what can be the polynomially growing subgroups in F2? And I told you something in the Leavitt's growth theorem that there are finitely many, and the sum of their rank is less than 2. And I think I said it, but I'm not sure now. I'm sure I didn't write it, and that's a mistake of mine. When the sum of the rank is 2, actually it is the whole group. There is no place for same rank pieces that are not the whole group. So, well, what can they be? They can be either the trivial group or an infinite cyclic group or F2 itself. Okay, let's just check something, that actually the commutator AB is preserved by all the Nielsen automorphisms, and they are supposed to generate the whole group. So there is at least one element that will not grow at all. So it cannot be that. It cannot be the trivial group. Then we are almost good, because if it is only so this a cyclic group, I explained to you that the 5 intimidating problems that I wrote on the board on the left were standardly solved when the polynomial groups were only cyclic. When only this group and its conjugate are polynomially growing, the reduction of last time concludes, allows to conclude. Meaning that if you give phi m size like that, the sumidary product will be relatively hyperbolic. Actually, we know what kind of group it is, with only abelian or almost abelian peripheral subgroups. And the analysis of the isomorphy problem between these groups will determine whether phi or psi are conjugate or not. And if it is the whole F2, well, actually, you need some help that I did not explain earlier. But in fact, the situation here is not so bad. The degree of growth is at most 1. And so it looks very much like a Nielsen automorphism itself, or generalizing this situation. So it does not explain very much how to do in this situation. It's just saying that this situation is not so adventurous. The degree of growth is always less than the rank -1. Solving the isomorphism problem between these two groups by the constraints of preserving the fiber and the orientation is the same as solving the conjugacy problem between the two defining automorphisms in-out. It could be. So that's really the isomorphism problem preserving the fiber. So here, I will just say that use some other story. And I will not explain it here for F2, but it's analyzing den twists and their roots. That's what I wanted to present as a first elementary point of view in this case. I wanted to say something more. Yeah, since we're still on this part of the board, I wanted to add one more ingredient about OT of F2 that's another story. So the group of automorphism of F2 quotients on outer automorphism of F2 by quotienting by the inner automorphisms. But in principle, it's well, not even in principle, it's not sufficient to solve in the quotient to know whether automorphism will be conjugate in OT. And that's a theorem of Bogopolsky. That the conjugacy problem in OT F2 is solvable. And then I don't have this initial trick to identify out F3 with a very nice group with a very nice geometry. I don't know how to do that. So I will use directly the strategy of looking for polynomially growing subgroups and analyzing the isomorphism between semi-direct products of F3 with Z. So what can be the polynomially growing subgroups? So what can be the polynomially growing subgroups in F3 for phi? So again, I will use that the sum of their rank is less than 3. And if it is equal to 3, actually the whole group is polynomially growing. So first possibility, only the trivial group. This will happen. This will be even generic in that case. Second possibility, one conjugacy class of a cyclic group. Call it G and its conjugates. Third possibility, two conjugacy classes of cyclic groups. Fourth, a rank 2 free subgroups. Its conjugates. And 5, well, F3 entirely. And there are no other possibilities, which is a little more than previously, but not so many. So again, so the three first give F3 semi-direct Z that is relatively hyperbolic with respect to a suspension of a cyclic group. So I realize I did not write both suspensions of a cyclic group, which is simply Z times Z, or Z semi-direct Z, with this guy reversing the orientation. So topologically, this is really the fundamental group of a torus, and this is the fundamental group of a Klein bottle. So in this case, as we already said, the problems, the 5 problems of the reduction of last time are solved. So we would know whether 2 automorphisms given in these 3 cases are conjugate or not. And it remains, we would also know, given an automorphism, we would also know whether or not it falls into one of these 3 cases. So first we check that both of them fall in the same case. Then we solve using the method of yesterday. And so we need to consider more those 2 last cases. And I will have to precise a second question, so that what can be the polynomial growing subgroups, and then what can be the growth in these polynomial growing subgroups. So in particular, in case, did not write numbering, I should write 1, 2, 3, 4, 5. In cases 4 and 5, what can be the growth in the polynomially growing subgroups? It will be the same answer, but I just want to write it. Because it allows me to put markers on, I don't know, labels on cases. So in case 4, it is either, so the rank of the polynomial subgroup is 2, so growth is either of degree 0 or 1. Degree 1, yeah, I'll come back to that, but I will not say anything. It's indeed, for those who know what it is, a root of a generalized N twist. And in case 5, we have degree 0, degree 1 possible, and degree 2 also possible, because the rank is 3. And I remember I did give you an example of quadratically growing automorphism. I think I did, yes. This is a nice enumeration. I should give at least pictures for examples in these cases before going further. So it's harder to draw an example of the first kind, and to have a picture of it. So it will be generic. The messier, the more likely it is in this case. So I'll rather draw an example of the second kind. And I will show you the free group of rank 3, but not in the graph way, but by taking torus minus a disk. This has fundamental group F2. So you remove a disk in the torus, if you think about it, when you draw the torus by identification. If you place a hole in it, it retracts nicely on the graph, generating F2. So no problem, it is F2, so it's not F3. And I add a loop like that, a single loop. So I hope you understand where is the surface, where is not the surface. I cannot shade it. And this now is F3. So I need to explain what can be an automorphism that would have only one single cyclic group as polynomial subgroup. Well, why not take an automorphism of F2 here, realized, for instance, by a pseudo-Anosov map of the surface, if you want it geometrically. It will preserve the conjugacy class of the boundary, which is the commutator earlier, this one, the commutator of the two generators of F2. So it will have exponential growth everywhere except on the conjugates of this commutator. And I still have to choose the image of the extra loop. And the extra loop I choose as image. So let me call it C, as choose as image C, followed by some loop in the surface. So what will happen to it? C will be sent to C, and then a loop that will grow exponentially fast under the pseudo-Anosov. So one part of it will grow fast, meaning that it cannot have polynomial growth. So for 3, I have to change my model for the fundamental group, for F3 as fundamental group, and I will choose the torus, but minus 2 disks. It is actually the torus minus in 1 disk, free product with Z. You can retract that on it easily. I mean, there's a mental exercise to check the retraction. And I can use again the fact that it is a surface to take an automorphism of the surface. Again, pseudo-Anosov. That will grow exponentially fast on the surface, except that it will have to preserve the two boundary components. Here, the two boundary components are actually two cyclic free factors, but they cannot be realized simultaneously as cyclic free factors. Each of them is one cyclic free factor in some free decomposition, but not in the same. For 4, the first case, well, I said it's suffices to take a finite order automorphism. So for instance, the symmetry here, the rotation by pi. And for the second case is, no, I'm not, no, this is not 4. 4 is, no, 4 is something else, sorry. 4, I will take again this model. And instead of wrapping C on itself followed by a crazy path in the surface, I wrap C on itself followed by some power of the loop. So here I have A and B generating the torus, the commutator, and I send C to C times AB, bracket AB to the K, so that this is fixed, so C will grow linearly. And C, AB will grow at most linearly. Meaning that some of its elements will grow less than linearly, and all of them will grow less than linearly. Some of its elements will grow with degree 0. Okay. So if I want to illustrate for the first case of 4, meaning that the degree of growth is 0 on the whole subgroup, I have to choose k equals 0, for instance. And 5, well, I already gave the example. I cannot draw it really. So A goes to A, B goes to BA, C goes to CB. Actually, I can play a little bit. I can make here a power, BA to the K, CB to the M, CB, to the K, C, B to the M. And it gives me many examples of quadratic growth. If K and M are non-zero. Okay, so that are illustrations of the different cases that can occur. And so I have already the 3 cases that are treated. I have the degree 0 and degree 1 case that will be given by a result that I'm not going to explain more, but I already mentioned it without saying earlier. So I want to evoke Lustig-Cohen and Lustig-Voigtman. The degree 0 and degree 1 polynomial growth. The conjugacy problem is solved for automorphisms of degree 0 or degree 1 polynomial growth. And this is because of the relation with roots of den twists. So now it's time for highlighting what are the remaining cases. 4 has not been treated yet, I should say, and 5 degree 2 has not been treated yet. That's the 2 remaining cases that needs to be treated now. I will draw them in orange here. And look, in both those cases, in the examples I gave, at least, there is something interesting. There is a free factor of rank 2 that is invariant. Here is a free factor of rank 2 that is invariant in the example 4. And here is a free factor of rank 2 that is invariant in example 5, quadratic growth. So my next statement is that it's not only on examples. Proposition. if phi is not almost toral, relatively hyperbolic, not in case, is in case 4 or 5 quadratic, then phi has an invariant conjugacy class of rank 2 free factor in F3. Okay, so this is slightly involved. It uses the elements of the RIPS machinery that was alluded last time. And I will not go into the detail of that. Instead, I will use that to finish these cases. Okay, that would be 3. Well, I will talk about now out of F2 star C, preserving the conjugacy class of F2. Okay, I'm looking at the outer automorphism preserving the conjugacy class. So I can always find a representative of them that preserve the free factor F2. Then it has to do something on C. And as a little earlier, the only thing it can do on C is sending C on some element of F2 times C times some element of F2. If it's more complicated, it's not going to be an automorphism. It's going not to be surjective. So this consideration leads to the following fact. That it is actually isomorphic to a semi-direct product and so I'm not finished, but I will explain what does an element like that do. So here an element like that would be some G phi 0. G phi 0, I want to apply it on F2 star C. So on F2, I will do phi 0. And on C, I will map it to C times G. But except that it could be sent on C inverse times G. And so there is another semi-direct product with Z over 2 here. And here would be, okay, it's slightly abusive what I write now, but meaning epsilon is equal to -1 or +1. So if we work with this decomposition of the group preserving a free factor of rank 2, we can find really equations for the conjugacy. we are given two triples like that in the iterated semi-direct product. And well, first thing first, we can assume that in the rightmost quotient, they are equal. We can assume that epsilon, epsilon prime are equal. And in the rest, I will take epsilon and epsilon prime equal to 1, because otherwise it messes a lot all the computation. And so we are looking for a conjugator. The conjugator has the form x k0 eta. And again, I will only look for a conjugator such that eta equals to 1, not to mess up all the computation. It's already a mess to do computation in a semi-direct product. I'm sure to make mistakes, perhaps I already did. And so, how does it work? Okay, so I have this element, so I will write only x k0, and I need to conjugate with this guy, so I just write what is its inverse. It's k0 inverse of x inverse, k0 inverse. And the equation to solve is the following. So I want to solve it in x and k0. So I'm given h psi 0, and it should be equal to, well, k0 inverse of x inverse k0 inverse. The other one is g phi 0. And on the right, I have x k0. So that's a computation in a semi-direct product. And this gives it gives that. Okay. What is it, all that? So x and g are elements of F2, my favorite free factor. Phi 0 is an automorphism of F2, so everything here is an element of F2, to which I apply an automorphism of F2. So here is really an element of F2. And here is just simply the conjugation of phi 0 by k0. So, what to look at? It's a fascinating piece of computation. What to look at? So, first we see that we are conjugating phi 0 to psi 0, which was to be expected. And actually, if the two elements were not conjugate in the first place, it was no need to continue. So, and I realized that I should have said that earlier. We could have first do a conjugation so that psi 0 is equal now to phi 0. So I add it here. Without loss of generality, we may assume psi 0 equals phi 0. So here we see that in this case, if we did this trick before, chi0 must live in the centralizer of phi 0. In hot F2. In all the cases of the that we are treated, the centralizer of phi 0 in out F2, which is just simply GL2Z, is virtually cyclic. Not in our example, in our cases. So after a finite index reduction, it means that actually chi0 is equal to phi 0 to the k composed with some inner automorphism that we write add y for add y inner. The conjugation by y. So, starting to be rather specific. I know that the computation is a bit long, but oh yeah, sure. To go to treat higher ranks, yeah, it will become this part. So the part where you will find an invariant rank 2 free factor is the part where the rank 3 makes yeah, not enough place for it for this to move. Yeah. But you will see that it comes into play again because we will, as we describe this this group, which has become our center of interest for the rest of the final computation. I know it's technical. This group involves out of F2, and we have to solve the conjugacy problem and problems in out of F2, which is feasible in out F2, but out F3 we don't know. That's answer. Okay, and so we have found a reduction to our element chi0 that is part of the unknown of the equation, and there is an extra constraint is that y must be fixed by phi 0. Okay, so I'm almost ready to wrap up, I think. Now I'm looking at the first coordinate of the equation that is on the right. I'm looking now at the orange part, and I will write what it has become. I place K0 on the other side, K0 of H. So remember H, I am given H. I'm looking for K0 and X is equal to X inverse G phi of X. And I replace the K0 by its value here. phi 0 to the k of h is equal to y inverse x inverse g phi 0 of x. I made the y go here, and because it's fixed by phi 0, it goes inside the parentheses. So now let's rewrite once again. Sorry, it's almost the last time that I rewrite this equation. So that's a much smaller equation. And that's almost the twisted conjugacy problem. I'm wondering whether h, or rather phi 0 to the k of h, is not conjugate, but twisted conjugate to g, and the twist comes from phi 0. So I'm still with this phi 0 to the k that is annoying, but actually it's completely harmless. So that is R, G, and phi 0 to the k of h, twisted conjugate. By phi 0. But actually, by a simple computation, I guess you have enough of the computation, but it's really syntactical. H and phi 0 to the k of h are themselves twisted conjugate by phi 0. And this is an equivalence relation. So actually, the real question is whether G and H, I can remove the phi 0 to the k here, whether G and H are twisted conjugate by phi 0. And this is a well-known problem that is has a nice solution due again to Bogopolsky, Martino, Maslakova, and Ventura. And I finish by this. Not. I'm only writing the initials, Bogopolsky, Martino, Maslakova, Ventura. And so we can solve this equation, and we are done. So we can decide whether the initial automorphism that we have now seen as automorphisms preserving a free factor of rank 2 are conjugate or not in out F3. Okay, I will stop there, and I thank you.
Are there questions?
Should that equation have G outside the parentheses? The last line at the right, in the middle one.
There.
The right side.
This side.
No,
That's a Y. Oh, here, completely here.
okay.
That's a Y. But Y is fixed by phi 0, so I can place it in here, so I can really see the twisted conjugacy.
Any other question? Okay, so if not,
you mean, Okay, so you assume that there are 3 factors of rank 3 that are preserved by conjugacy? I don't know. No, I don't know. I don't know if I can do that. So in principle, you could expect to have I mean, if you want to analyze the semi-direct products, you could expect to have a relative hyperbolicity with what happens inside the free group F3, but it can be glued together in some weird way. And to understand how it's glued, you have to solve the infamous 5 problems of last time in the intermediate peripheral subgroups. So perhaps I'm missing some things, some easy shortcut, but I'm not sure. Yeah, maybe you can discuss later.
Any other question? Okay, so let's thank the speaker for the mini course. Let's thank them.